Recording is up and running. Cool. So everyone should be able to see the screen. So first things first, we will go over the sheets that I gave you in the Google Drive last week. So the first section was a true-false. So lines of force never cross, which is true. Force lines never cross. Like magnetic fields attract? No. So we talked about last week, like poles and like fields don't attract. They repel each other. Magnetic field can be plotted using a compass. It can. The poles of a magnet are of equal strength. Yes. A magnet cannot have poles of different strength because it is considered one magnet. Well, unlike magnetic poles attract, yes, they do. So a north and south pole will attract. And the direction of lines of force are north to south. So they leave the North Pole and flow to the South Pole. This is true. And the South Pole of a magnet always tries to point north. Yes. Cool. So this is what the flux lines would look like between the pole faces, indicating the direction of flux lines. So only the ones going directly between the North and South Pole were the ones we wanted you to put up. Cool. And this is what the magnetic flux lines would look around a permanent magnet. If you had something along these lines, cool. So in this picture, pole A and B are both north poles because the flux lines are not joining, they are repelling each other. And this is what a two bar magnets opposite directions to each other would look like, with a dead spot in the middle noted by X, and the flux lines flowing from north to south around each magnet and between north and south of each magnet itself. Cool. So those were the pictures. And then moving on to the equations. So the equations for the equation we needed for this, or the formula, was EMF equals LVB, or any combination of BLV, BVL, which is basically the electromagnetic force is equal to the length times the velocity times the magnetic field measured in Teslas, or the flux density. So for this one, it was 0.9 because 90 centimeters becomes 0.9 meters. So 0.9 times 2.7, because centimeters per second, 270 becomes 2.7 meters per second, which ends in a EMF of 4.374 volts. So for the next question, we needed to rearrange the formula. So we needed to divide both sides by EMF, and then divide both sides by B, or take away B. So we just move the B to the other side. So it's LV divided by EMF, which gives us 0.22 times 5, because 22 centimeters is 0.22 meters, divided by 0.33, because 330 millivolts is 0.33 volts, which means we have 1.1 divided by 0.33, which gives us 3.333 Teslas, rounded to 3 decimal places, like the instructions at the top say. Cool. Question 3. So we're just changing around with V equals LB divided by EMF, 0.4 times 0.085 divided by 0.34, or 0.034 divided by 0.34, which gives us 1 millisecond, or we can convert that to 10 centimeters per second. So 1 meter per second or 10 centimeters per second. Cool. So a conductor, which is moved perpendicularly through a magnetic field, flux density 4.9 milliteslas, velocity of 16 milliseconds, and a induced EMF of 39.2 millivolts. So calculate the length of conductor. So rearranging the formula, L equals VB divided by EMF. So 16 times 0.0049, because 4.9 milliteslas results in 0.0049 teslas, and then divided by 0.0392, because 39.2 millivolts becomes 0.0392 volts, which gives us. So good, guys. If you're struggling with internet or anything, the recording will be up later. Hopefully it sorts it out by the time we get to the main topics. So 0.0784 divided by 0.0392, which gives us 2 meters. So this is the kind of way we work through these questions, but the questions on the next page are basically the same with different values. So we'll just go through the answers. So question 5, we ended up with 1.617 volts. Question 6, we ended up with 10.25 teslas. Question 7, we ended up with 0.071 meters per second, or it would be 7.1 centimeters per second. And then we end up with 1.503 meters, 3 decimal places. So those were the answers to the questions from last week. Again, everything will be available on YouTube after this. But for now, we'll go through tonight's topic. So we're going to carry on with our topic of magnetism. Magnetism is a helpful thing in the electrical industry because it allows us to change and transfer voltages, as well as it gives us the ability to create rotating machines, such as motors. Motors and transformers all rely on magnetism. So that's a huge thing. So obviously in generation and distribution, we use magnetism to generate electricity with a rotating machine, distribute it with transformers, which then can be used by motors at the other end to do manufacturing. Cool. Cool. So electricity and magnetism. So when a current flows in a conductor, a magnetic field is produced around that conductor. When an EMF is applied to the conductor and a current flows through it, the iron filings will become affected by the magnetic field that becomes present around the conductor. They align themselves with the flux lines as the flux lines circle the conductor, like shown in the picture. So the flux lines are perpendicular to the flow of current and go around the conductor in a circular pattern. Cool. So the polarity of the field can be determined by examining the direction of conventional current into the end of the coil. So south, it is rotating in apparent clockwise. So conventional current flowing in a clockwise direction indicates a south pole, and anti-clockwise flow indicates a north pole. Cool. If you look back at the diagram, you can see that the magnetic field is perpendicular to the conductor. That is, it's at 90 degrees to the conductor. So the current was flowing from up to down in a conductor on the page. The magnetic flux would have to be coming out of the page towards us and extend down through the page. So this is how we represent it when we do questions and diagrams. So current entering the paper looks like the end of a dart or arrow. Current exiting the paper looks like the point of dart or arrow. So if you see a plus, it's like looking at the back of the arrow, it's flying away from you. Looking at a dot, it's the arrow coming towards you. So this is a cross section of the conductors. Is this making sense so far, guys? First slide. Okay. Yeah. current flows in conductor, magnetic field is produced. So the EMF applied to the conductor, current flows through it, iron filings will become, so this is what we see when we put magnetic filings on a piece of paper. So imagine a piece of paper or timber or some form of medium with a conductor flowing through it. If we were to pass current through that conductor and have iron filings on the surface, they would arrange themselves in rings like is shown on this. Remember, guys, if I go too fast, it will all be up on YouTube. Yeah. Yeah, like we talked, polarity of the field. So if the magnetic field is going clockwise, it's a south pole. If it's going anti-clockwise, it's a north pole. And this is the way we tell if the current is flowing into the paper or out of the paper. So we can use our corkscrew or right-hand grip rule, which we will talk about now. So as we've seen, current flowing conductor is accompanied by a concentric magnetic field. We can find the direction of these fields by using small compass needles. If conventional current is moving away from you, that is into the paper, then the direction of the field is clockwise. The corkscrew rule will help you remember this because to make a corkscrew in a forward direction, you must rotate it clockwise. So if the current is flowing away from us and we're using the corkscrew, it's to the right. If the current is flowing towards us, it is moving to the left, or the corkscrew will be going anti-clockwise. Does that make sense? Okay, ignore that. And then we can also use the right hand grip rule. So instead of using the corkscrew, we can look at the current carrying conductor. We can grab it with our right hand. If the current is flowing up, as indicated in the picture, then the current is going around, the magnetic field is flowing around in a, I guess you call that anti-clockwise if we were looking at our thumb. If the thumb is pointing away, it'll be clockwise. If the thumb is pointing towards us, it'll be, yep, very similar to lefty-loosey, righty-tighty. We can also use this to grab a electromagnetic or bar magnet. So if we grab the bar magnet and our thumbs are going in the way of the current flow in terms of a DC current, then we can use our thumb to point towards north. So if our fingers are grasping the way that the current is flowing, then we can use our thumb to figure out the north pole. Cool. So this is just another illustration of the way that where current is flowing into the paper, it's going clockwise. The current is flowing out of the paper, it's going anti-clockwise. Cool. So lines of flux never cross. If we had two cables sitting next to each other, their magnetic fields would repel each other. See, they're hitting each other when they get close. If we had two cables sitting next to each other, their magnetic field would attract each other. See, the magnetic lines are lining up, they would actually pull towards each other. So we have cables that the current is going the same direction, they will repel each other. If we have cables with current going the opposite direction, they will attract each other. Obviously, if we have AC current, these magnetic fields are being generated and destroyed 100 times a second because of, you will learn what we will learn about AC waveforms next week. Cool. So No matter the circumstance, there is always a magnetic field when there is current flow. However, the magnetic field is of little use to us in industry other than the fact we need to be wary of it when running cables together. So in terms of when current is flowing in a cable, unless we are using it to make a transformer or use it in a motor or a relay or a solenoid or the very many other uses for it that we use it, current flowing through a general cable is of no use to us. So we take right hand like we talked about and grab the bar or the cable and turn it so that our fingers are now pointed around the coil in the direction of current flow. The thumb is pointing in the direction of flux lines or towards the north pole of the magnet. So you can determine the magnetic polarity of the electromagnetic magnet or solenoid with this rule if it is a DC magnet, bar magnet, or DC solenoid. Cool. So if we have a coil of wire without any form of bar in it, this is what the magnetic flux lines would look like. Cool. So if we remove the core and take a sectional view through the coil, we can see that the field is made up of individual circles of flux which surround the wire of the coil when a current is flowing. So we can see the current flowing into the page at the top and out of the page at the bottom, and the way that the magnetic flux lines interact, creating a north and south pole inside the coil. Here we have I don't know how well it's showing up on your end, but a diagram showing that. Cool. So in reality, a solenoid is wound many more times around an iron core or a former. This makes the magnetic field stronger for two reasons. The more turns of wire wrapped around the former, the more magnetic flux the former is subjected to, and the magnetic flux concentrates in the former as if as it offers a path of less reluctance as opposed to the air around the outside of the coil. And we talked about last week, reluctance is the opposition to a material willing to have a magnetic field induced into it. So the strength of the electromagnetic is determined by a few things, such as the number of turns, the current flowing, and the reluctance of the core. We do not need to know how to calculate these values. However, the end result gives us a value of magnetic field strength measured in Teslas, of which we will be given and used in other calculations later. Cool. So magnetic forces. So one such application is the electrically operated switch known as a relay. So using a relay, a small current in the coil circuit can control a much larger current in an external circuit. The operation of the relay can be explained by reference to the diagram below. So here we've got fixed contacts, which are operated by which have a common, a normally open and a normally closed. And you have an armature on a pivot point that pushes up on the movable contact. If we apply a voltage and current to the coil, that will energize and create a magnetic electromagnet in the former, pulling the armature towards it, which will then push that movable contact up, thus creating a remotely controlled electric switch that does not rely on Wi-Fi. So, how many of you guys use relays day to day, or have used a relay in your work so far as an electrical apprentice? Seen one? Yep. Cool. So we're talking relay in terms of a relay that you would see in a switchboard, but what about the relays for bathroom fans? Or the run-on timer relays? So just because the relay doesn't necessarily have to look like the picture here, they come in all shapes and sizes. It is basically an electric switch. There are relays, very small ones, inside of sensors. If you open them apart, you'll find a small, tiny relay inside them. Cool. So the current flowing in the coil causes the iron core to become magnetized. The magnetized core then attracts the moving armature, which is balanced on a knife edge of the yoke. When the armature moves, a piece of insulating material pushes against a set of contacts, causing them both to touch. Not everyone gets to work with relays, but because of your apprenticeship, hopefully you do, just because you will need to do it for some of your on jobs. Cool. So when the current flowing in the coil is switched off, the iron core is demagnetized, and so the armature returns to its original position, releasing the pressure from the contacts. Cool. There are normally three ways of arranging the contacts. Normally open, so that they close and make a connection. Normally closed, so that they open and break the connection. Or changeover, where the center contact moves from left to right or right to left, depending on which magnet is energized. So a relay may have two coils in it instead of just one. Cool. So normally open, normally closed contacts are normally used for things like lighting controls, speakers, lifting magnets. There are all kinds of things we can use relays for. So there are all kinds of uses for magnetism like this. So we talked about, motors rely on magnetism. We've got generators, transformers, lifting magnets, or large electromagnetics. So the way speakers work is it uses a coil inside of the speaker to basically move the speaker cone backwards and forwards, generating sound waves. That's how we get sound out of speakers. Relays, like we talked about, so buzzers and bells. So old school doorbells or fire alarm bells. Oh, yeah, and school bells. One part of your apprenticeship used to have to, back in the day, design a school bell or fire alarm bell circuit. And solenoids. So solenoids are a lot like relays, but they're actuators using electromagnetic to move a rod or plunger. So they're used more in door locks and control valves, or one of the most recent ones that I've worked on with a friend was a solenoid that controlled a locking mechanism for a car lift, or a car stacker. So there are all kinds of uses for electromagnetism inside the electrical industry, and it'll become more and more common to see it as you go through your apprenticeship. Cool. So now we'll move on to talk a little bit electromagnetic induction. So electromagnetic induction, can you guys give me a brief kind of description or definition of what you think electromagnetism is? Or what do you think electromagnetic induction is? Like that, Timothy. Okay, some interesting answers. Keep them coming while I talk. So electromagnetism is the magnetism created by electric current flow. So when we talk about electromagnetism, we're talking about the magnetism that is created by electricity. When we're talking about electromagnetic induction, we're talking about using electric current flow to create a magnetic field, which then induces a EMF and therefore current flow in another conductor. So if we talk about the most common form of induction that most people talk about these days is a induction hob. So the way an induction hob works is basically you've got one side of the essentially a transformer, or it's a coil of wire um, inside a inside of the hob, which then creates a EMF inside of a ferrous material on top of the stove, which is why when you have a induction hob, you can't use copper or aluminium because they are good conductors, whereas something like stainless steel or cast iron, they're very poor conductors, so they have a very high resistance. This is why they become hot when you use a induction hob, because the resistance causes heat buildup, which means you can cook on it. That's the basic principle of how an induction hob works. Cool. So when we start talking about electromagnetic induction, we have to start talking about the Sparky gang signs. So the first one we look at is the Fleming's left-hand rule. So we take each finger, being a thumb, index, and middle finger at 90 degrees to each other, like the picture. Cool. So the left-hand rule is for motors. Cool. So force is your thumb. It is the force induced on the rotor or conductor. Cool. B is the magnetic field. This is the strength of the field. C is the current. This is the amount of current induced in the conductor or rotor as it passes through the field. So if we use our finger to point from north to south, and we use force, so whether the winding or coil inside of the magnetic field is going up or down, and then we know which direction the current is going. So we hold our hand in front of us and we point the force up because the rotor is going up and clockwise, but the magnetic field is going from left to right, north to south. The current would be flowing towards us. But if we then take that same rotor and it's going pointing down, the rotor is now pointing down, but the magnetic field is, or the rotor is now traveling downwards, but the magnetic field hasn't changed. The current is now flowing away from us. Does this make sense? Okay. Okay, I'm just trying to find a graphic to show you guys. So the left hand is for motors, and then we use the right hand for generators. So if we go to the next slide, cool. So the right hand rule. So the right hand rule is for generators. So we've seen that an EMF is induced or created across the ends of any conductor, which is forced through a magnetic field. If we connect a load across the conductor, a current will flow through it. The size of magnitude of the current can be calculated using Ohm's law. The direction can be found using Fleming's right-hand rule. So if the thumb is the motion of the conductor, index finger is the magnetic field, we can determine the current. So we use the right hand for generators and the left hand for motors. So we generate is the best way to remember it. So generate, and we use what's left for the motor. So generation with the right hand, we use what's left for the motor. And it's very, very kind of lame way to remember it, but that is the way that we need to remember it. Trying to find a good picture of a single wire generator to good picture to show you guys what I am talking about. So if we were to look at a loop generator, so we can see that the magnetic field is flowing across that way. So if we were to treat this as a motor instead, we use our index finger for the lines, and we know that, for example, that red conductor is going to move up. So we can point our thumb upwards, we can point our index finger in the direction of the magnetic flux. So we know the current flowing through that red side of the wire, if this was a motor, would be flowing towards us. Now, if we were to treat this as a generator like it is, we would have to try and point our index finger from north to south. And if the red is going up, then the current would be flowing away from us. I know it's awkward to kind of spin your hand around, but if you point your finger towards your screen, you point your index finger from north to south, and if the red conductor is moving upwards, then we know the current is flowing away from us in the red conductor. Is that making a little bit more sense to some people? It isn't in terms of the actual way this is going. It's actually the blue conductor. I am just using it as an example. It will tell you in the question or show you that it's moving right or left. So if we look at the purple arrow at the bottom, it says the axis of rotation. It means that the blue is going up. You only need to know which way it's spinning, and it will ask you which direction is the current flowing. Is it flowing from red to blue or blue to red? So if we look at the blue wire this time, we know that the axis of rotation is going anti-clockwise. So we know the blue is going up. We know that the magnetic flux is going from north to south. And so if we align our fingers, we can tell that in this generator, because we're using a generator right hand, that the current should be flowing from blue to red. If the generator is spinning anti-clockwise. Does that make a bit more sense, Sean? Okay, yeah, it does make a little bit more sense if you read through the SCORM packets at your own time. I'm just trying to provide you guys with a little bit of extra knowledge. All good, Levi. You'll be able to catch up on the video on YouTube a bit later. So we will look at this generation stuff a little bit later on. Right now, we are just looking at a couple of the basic rules. So if we go back to the right-hand rule. So this conductor is going to pass through a magnetic field. If red is north and blue is south, what direction would the current flow be if it is going to go downwards through the magnetic field? Is the current flow going to be towards or away from us using the right-hand rule? Um, as we move the conductor downwards through the magnetic field, the current flows away. Passing a conductor through a magnetic field, if red is north and blue is south, what direction will the current flow if we go the opposite way? So we would think it would go the other way. Cool. So when the conductor passes through the magnetic field, a current will be induced into it. Also, a magnetic field will be created around the conductor. If the conductor is moved down through the magnetic field like previously, which direction will the magnetic field move around the conductor if the current is flowing away? Yeah, I actually think this was wrong. Let's see if I can get this going. Where's the chip? Where's my camera off? Okay, cool. So I think when this PowerPoint was made, it was not done very well. So and you guys just making sure you can actually still see me. Can you still see me on your guys' screen if I stop sharing? Cool. So you should still be able to see me, and I've spotlighted it. Cool. So I actually think the image on the screen was wrong. So if we were to use the generator rule, because we're passing inductor through a magnetic field, so the first thing we do is we take our index finger and we point it in the direction of the magnetic field. And we know our thumb, because the conductor is moving down, we kind of need to invert it, and then our index finger will be pointing towards us. Okay, so the on-screen picture is actually wrong. The current would be flowing towards us. And you see how ridiculous this looks? This is what I looked like when I was doing my tests and exams using this rule. So yeah, it would actually be flowing. So the PowerPoint is wrong because the PowerPoint says that it is flowing away from us. So this is actually wrong. It was PowerPoint. It needs to be fixed. But if we go in the opposite direction, we know magnetic field is still going this way. The direction of the conductor is going to go upwards. So we know that the current should actually be flowing into the image. No, so this is the way it looks. Okay, it's why we've nicknamed it the Sparky gang signs, because it does look like I'm trying to do some half-assed lame gang sign. I'm not trying to say that gangs are lame. I'm trying to say that I am, and proud of it. Cool. So yeah, again, for the next one, the direction of the conductor is going to move up. The magnetic field hasn't changed. So our conductor should actually be going into the page. So instead of a dot, in the wrong way. So instead of a dot, it should actually be an X. Cool. So now, with this rule, the conductor passed through the magnetic field, current will be induced into it. Also, a magnetic field will be created around the conductor. So if we move the conductor down through the magnetic field like previously, which direction will the magnetic field move around the conductor? So if we use the right-hand grasp rule, cool. So remember the right-hand grip rule? So for the right-hand grip rule, we take our hand, we wrap it around the conductor, and our thumb points in the direction of the current flow, in this case in. So the conductor, hold on, sorry, there's sensors in this room. So I have been having to get up every once in a while to make sure the lights stay on. I don't know what they were thinking when they designed this place. So yeah, if our current is flowing in, it means that our field will be going clockwise. So as we move the conductor down through the field, cool. So lines of flux do not cross, but bend around each other. So as we induce the current, it will actually push the conductor in a certain direction. In this case, it would push it downwards because of the way the flux lines would form around the conductor that is moving. Excuse me. Cool. So motion in a magnetic field. So when a conductor is moved through a magnetic field, an EMF is generated across the ends of it. It is important to remember that an EMF is only generated whilst the conductor is within the magnetic field, and only the parts of the conductor exposed to the field lines are a part of the generation. There are other factors that determine EMF generated. So we look at EMF generation. If we consider the vertical movement as being at 90 degrees to the field, we must consider the horizontal movement to be at 0 degrees. That meaning when we go this way, 90 degrees to the field, it's the horizontal movement is at 0 degrees to the magnetic field. So 90 degrees and 0 degrees. So we're only generating when we're going up and down through the magnetic field, If we move side to side inside the magnetic field, we get no EMF because we are not moving through flux lines. Cool. So a conductor moving at right angles to the field, it induces maximum EMF in the conductor. A conductor moving in line with the fields cuts no lines, and so no EMF is induced. Does that make sense? That we only generate an EMF when we cut through the magnetic flux lines? This will become quite important later when we start talking about the AC sine wave, and the way it is produced and the way it goes through positive, negative, and zero volt points. Cool. So everyone remembers trigonometry? So before we consider EMF induced in a conductor moving at angles other than 90 degrees in a magnetic field, we must first consider some trigonometrical ratios found in a right angle triangle. So right angle triangles are everywhere in electrical theory. So yeah, good to brush up on trigonometry. So a right angle triangle. So the three angles in a triangle all add up to 180 degrees. If one of the angles is a right angle at 90, it follows that the other two must also equal 90. So if one of the remaining angles is 60, the other must be 30. If one angle is 74, the other must be 16, etc. If one angle increases, the other must decrease, and vice versa. So we normal label each angle using a capital letter, and the side opposite each angle with the same letter in the lowercase. So this is shown in the picture where angle C is the right angle. So using angle A as a reference, the side B called the adjacent side, the side A is called the opposite side, and C, the largest side, is always the hypotenuse. So if we use angle B as a reference, side C is still called the hypotenuse, but the side A is now the adjacent side, and side B the opposite side. So this leads us into the SOHCAHTOA relationship. Cool. So the ratio of these sides, one to another, are constant for any angle in a right angle triangle. These ratios are defined as what you see on the screen. I won't go through them all, but basically the sine of angle A is side A divided by C, cosine A, B divided by C, tangent A divided by B. It's always sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. So this is the way that SOHCAHTOA comes about. Sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. So in this, for a lot of electrical, we're mainly interested in the sine ratio for sine waves, but the others are important in other aspects of electrical, which you'll do a little bit more about in years 2 and 3. But for now, how many of you guys have seen the sine waveform before? Cool. So this is a sine wave, and it is the waveform that is for AC voltage, and we also use it for current, but mostly voltage. So the way it is represented here, so if we look at the numbers along the middle here, they are basically angles. So we've got 0 degrees here, all the way to 90 degrees here, 180 in the middle, all the way through to 360 degrees. These represent the angles of basically angles of incidence or angles that the generator is spinning, basically from 0 to 180 and from 180 to 360. So the sine wave is a representation of the coils of the generator cutting through a magnetic field, going from 0 degrees being flat to 180 degrees being flat again, and then back to 360 being flat again. So as we get to 90 degrees, so we know that at 90 degrees we cut the magnetic field at the highest amount. So therefore we have the highest voltage or the highest point of the sine wave. And then again at 180 plus 290, 180 plus 90, so 270, we have another peak inverse voltage. Again, this will become a lot more relevant as we go on through the theory, but basically we can figure out, depending on what point the rotor or coil is cutting the magnetic field, the voltage that is induced. Is anyone not getting what I'm meaning by that? If it's not making sense, I can stop and try again. But I just want to make sure everyone understands what I'm talking about in terms of this being generation. Okay. So we'll move on to the next one. So EMF generation. So now that we've figured out that an angle makes a difference, we can modify the equation E equals BLV or LVB that we were using to take max EMF in the positive and negative sign of the sine wave. That's really good, Timothy. Thanks for posting that one. So yeah, as it spins, it peaks, goes back to the middle, troughs, middle or zero. Yeah. So, so that's always a good one. So we will learn about that when we get to generation, but it's just good for you guys to know about it now because we can take into account of movements of the conductor at angles other than 90 degrees. So in the sketch, lines depicting the lines of flux have been omitted for clarity. So 3 directions of movement are indicated: vertical, horizontal, and also at an angle 0 degrees to the horizontal. So theta, it's the Greek letter. Theta is a letter which is commonly used to indicate the size of an unspecified angle. So normally when you get a theta symbol, it's basically saying unknown angle or angle yet to be determined. So with the sketch shows with the addition of a parallel vertical line, theta is an angle in a right angle triangle. Sweet, all good, Ryan. Just be sure to jump on YouTube at some point tomorrow and watch the video. Hold on, before you go, sorry, I will get right back to that. I'm going to give the link for the homework for this week. Come on. Share, copy link. Let's make sure you guys. I will just make sure. Yep. So quickly download that if you can, or then now that you're in the chat, you can see it. So that is the stuff I want you guys to try and look over for next week. Damn it. Sorry for this. Cool. So the amount of voltage induced in the conductor is proportional to the vertical components of the velocity. And this, of course, the hypotenuse multiplied by the sine of angle theta. No, homework doesn't. It's more a case of it's just something to give you guys a chance to expand and practice. So obviously go through the SCORM and Hive. That's more important. But if you guys want to do the extra study, and I go through it anyway, so you guys have the answers, it's just extra knowledge to give you more tools to use in case they throw a weird question at you. So no, I don't check if you guys did the homework. I just give you the answers for it later. So yeah, so multiplied by the sine of angle theta. So the equation for the EMF induced by a conductor cutting a magnetic field at a right angle is E equals BLV volts, modified for any cutting angle to E equals BLV, or magnetic field, times by length of conductor times by velocity, multiplied by sine theta, and is represented in volts. So generated EMF is E, which is voltage. The strength of the magnetic field is B, measured in Teslas. The speed the conductor passes through the magnetic field is V, velocity. And the length of the conductor in the field, L, length. So EMF is always measured in volts, and angle of direction through the field, sine theta. So EMF is always measured in voltage or volts. The strength of the magnetic field is Teslas. The speed the conductor passes through the magnetic field is meters per second. So if you get any other value other than meters, say for example centimeters or kilometers per second, or even kilometers per hour, you will need to then multiply those kilometers by 1,000 to get meters, and then divide by 60, and then 60 again to get seconds. And then length of conductor in meters. So if it's in millimeters or centimeters, you will need to convert it into meters. And the angle is always given as an angle. You shouldn't need to change too much of it, unless it's 90 degrees, in which case it is just 1. Cool. So E equals BLV sine theta. If the conductor is passing at 90, we can ignore the sine theta. So you put it into calculator as sine 90. This will equal 1. Yep. Speed is always measured in meters per second. So if you get it in any other format, you'll need to transfer it to meters per second. God damn these lights. Sorry guys, lights again. Cool. So uh, hopefully everyone can see the calculator. So when we're talking about using sine, if you didn't know, this is the sine button here on the calculator. So we put in sine 90. So sine 90, it equals 1. So whenever you get a sine, so for example, if we get sine 45, it's 0.707106. That is what sine of 45 degrees is. I think it's, yeah, so sine of 30 degrees is 0.5. So at 30 degrees, it's half the voltage. Cool. So now let's try and put it into practice. So I will put the question up, and then I'll let you guys have a stab at trying to use the formula. So the EMF induced in a conductor length of 40 centimeters, which would be 0.4 meters, when it is moved through a magnetic field flux density of 500 milliteslas, or 0.5 teslas, at a velocity of 75 centimeters per second, or 0.75 meters per second, at an angle of sine 45 to the horizontal. What is the induced EMF in that? I'll give you guys a little bit to try and grab that. Remembering our formula, E equals BLV sine theta. Okay, so we got one answer. Yeah, using an iPhone calculator might be a little bit easier, a little bit tricky. Cool. So we'll go through it. Just keep plugging in your answers to the Teams chat. Just so it's a lot easier to prove you guys were attending. Yeah. Cool. So it ends up being 500 times 10 to the minus 3, which gives us zero point 0.5 Teslas. 40 times 10 to the minus 2, which gives us 0.4 meters instead of centimeters. And 75 times 10 to the minus 2 to convert from 75 centimeters a second to 0.75 times the sine of 45 degrees, which gives us 0.106 volts or 106 millivolts. Okay. Yeah, if you're using an iPhone calculator or a phone calculator, the best thing I can say is convert the units first, write them down, and then do the multiplication one step at a time. And then the sine 45 might be the tricky one. Cool. So passing the conductor at 90 degrees, sine 90 equals 1. Okay, so going back to the answer. So when we say 10 to the minus 3, that is multiply or dividing it by 1,000. So when we multiply, hold on, give me a second. Let's turn my camera back on. Cool. So when we take 500 times, oh, where am I going? Cool. So when we take 500 and times it by times 10 to the negative 3, it's the same as dividing it by 1,000. So milliteslas, um, so it's just milli. So I don't know where you got that spelling from, but millimeters. So yeah, taking meters and changing it to, so yeah, when we take millimeters and change it to meters, we divide by 1,000, which is the same as multiplying it by 10 to the minus 3. It's just a way of writing the equation. So if we shift the decimal 3 points or divide by 1,000, we can times 10 to the minus 3. And then so if I were to take 0.5 and then 0.5, cool. So we have a 0.5 here. So we can see the 0.5. If I push this ENG or engineering button, that'll shift it. So 0.5 is actually 500 times 10 to the minus 3. It is just a way of writing it in a calculation or a way that the calculator can understand so that we can quickly type it into a calculator. So by changing 500, when we do times 10 to the minus 3, we are dividing it by 1,000. So we're changing the milliteslas into teslas by dividing it by 1,000. Does that make sense, Sean? Sorry, you're wondering why I'm looking over this way. I've got two computers with the chat open so I can monitor everything. Okay, I don't know if you are putting it in wrong, but when I put in 500 milliteslas to teslas, I get 0.5 using that link that you sent me. Um, yeah. So when I, yeah, I changed it. I don't think you may have been. Okay, so it comes up with a syntax error. Are you entering the calculation as it is? So when we do this calculation, the best thing to do is use brackets. So bracket 500 times 10. So the best way to do it is use this times 10 button here at the bottom of your calculator. So, and then you put the negative, and the best way to do the negative for this is to use, there's a negative button here. So negative 3 bracket times bracket 40 times 10 to the negative 2 bracket multiplied by bracket 75 times 10 to the negative 2 bracket times sine 45, and then don't close the bracket and then hit equals. So you should have a calculation that looks in your calculator like this. So 500 in brackets times 10 to the minus 3 times in brackets 40 times 10 to the negative 2 in brackets times in brackets 75 times 10 to the negative 2 times sine of 45. Yeah, I know it's the long way to write it out, but it means that you don't get the syntax error. But this is good, guys. Good solving problems, so that way it makes sense for you and you learn to use your calculator now. I know this would be a lot easier in person, and I'm sorry that it is an online class. There isn't a lot I can do, but hopefully I will get to catch up with you guys when you come for block course. So we've got, another 2 weeks after this, and then the first lot of you are down for your block course, and then a week break, and then the week after that, the next group of you. So hopefully we'll get to at least say hi to the majority of you when you guys come down for block course. But I will be back in Wellington after this week. Still not sure how I feel about it. Cool. So lights going out again. Cool. So the passing a conductor at 90 degrees gives us sine of 1. If we pass the conductor at 45 degrees, we get a sine of 45, which is equal to 0.707. And then if we pass the conductor at 0 degrees, we get sine of 0. What is the sine of 0? Yep, the sine of 0 is 0. Now the question is, how many of you guys put that into a calculator? I'm joking, it's fine, guys. I would have double checked too. Cool, so yeah, 0 degrees. So now that we've had a go at 1, we'll calculate the EMF induced in a conductor with a length of 55 centimeters. So centimeters, we're going to times 10 to the negative 2. When it's moved through a magnetic field of flux density 625 milliteslas. So we're going to times 10 to the negative 3 for this. Velocity of 87 centimeters per second. So this is going to be 10 to the minus 2 at an angle of 39 degrees to the horizontal. So if we still have the equation in our calculators, which I cleared my calculator, so I'm going to have to type it in all over again. But that's fine. Good practice. Let me know what you guys get. Okay, Cody, you might want to go back and check the values that you use because, yep, 0.118 volts. Yep. Yep. Cool. Yeah. So we go over our formula again. So we have E equals BLV sine of theta, which gives us 625 times 10 to the negative 3, 55 times 10 to the negative 2, and 87 times 10 to the negative 2 times sine 39 degrees. This then gives us 0.188 or 188 millivolts.